In section 9.2, we talk about the real numbers. So a set is a collection of objects. For our purposes, we will most often be considering sets of numbers. One way to name a set uses what is called roster notation. So for example, roster notation for a set containing the numbers 0, 2, and 5 would just be the curly bracket 0, 2, 5, and then close it with the other one. Sets that are part of other sets are called subsets. In this section, we become acquainted with the set of real numbers and its various subsets. So the first one is the natural numbers. These are the numbers that we learn as kids. The counting numbers, so 1, 2, 3, 4, so on and so forth. The next set is whole numbers. And so the only difference between natural numbers and whole numbers is the fact that in the whole numbers, we include the number 0. So it's still the natural numbers, but we've just tacked on a 0 at the beginning. And so we can represent these on a number line. And the natural numbers start from 1. So this is something people mix up all the time. Natural numbers don't include 0, whole numbers do. So we can create a new set called the integers, and we start by having the whole numbers, 0, 1, 2, 3, and so on. And for each natural number, we obtain a new number to the left of 0 on the number line. So for the number 1, there will be an opposite number, -1. For the number 2, there will be an opposite number, -2. And we keep repeating this process. This gives us the set of integers. And so that includes numbers like -5, -4, down to 0, and then 1, 2, 3, 4, 5. And so we call -1 and 1 opposites. And 0 is its own opposite. And 0 is neither positive or negative. Now, pairs of opposite numbers are the same distance from 0. The integers extend infinitely on the number line to the left and to the right of 0. So let's go ahead and look at example number 1. We're talking about integers in the real world. So tell which integers correspond to this situation. Hal owns a stock whose price decreased $16 per share over a recent period. He owns another stock whose price increased $2 per share over the same period. So what integer would correspond with a $16 decrease, and what integer would correspond with a $2 increase? So we would use -16 for the decrease, and we would use 2 for the increase. We don't write plus for its sign, we just write 2. Now let's talk about another set of numbers. This is even larger, and this is the set of rational numbers. And so we start to consider quotients with integers as long as we don't have 0 division. So the following are some examples of rational numbers. 2/3, -2/3, 4 is 1 because we can always write this with a denominator of 1. Same thing goes with 0. 23 divided by -8, -0.17, and 10.5. So all these are examples of rational numbers. And just as a tip, we can write a negative and a fraction in 3 different ways. We can either write it out front, in front of the fraction bar. We can write it on the top, or we can write it on the bottom. All 3 of these are equivalent. And so the set of rational numbers is the set of numbers a over b, where a and b are integers, and b is not equal to 0, because we can never divide by 0. And so this new set of numbers contains the whole numbers, the integers, the arithmetic numbers, which is the non-negative rational numbers, and then the negative rational numbers. And so on the number line below, you can see where these numbers would fall at. These are all rational numbers. And so to graph a number means to find and mark its point on the number line. So let's graph each number on the number line. We've got negative 3.2 and 13 over 8. Let's start with negative 3.2. So I'm going to use a pink dot to distinguish. So because it's negative, that means it's going to be to the left of 0. So we're coming over to negative 3. Now is negative 3.2 going to be to the left of negative 3 or to the right of negative 3? It's going to be to the left. It's going to be between negative 3 and negative 4. What about 13 over 8? Let's go ahead and make this a decimal so it's a little bit easier to plot. Well, 13 over 8, when I plug it into my calculator, I get 1.625. And so because it's positive, that's going to be to the right of 0. And 1.625 is going to be a little bit more than halfway between 1 and 2. And so each rational number can be named using either fraction notation or decimal notation. So we're going to convert the fractions to decimals first. So looking at negative 5 over 8, we're going to go way back to long division. Everybody's favorite. So we're going to just ignore that negative out front until we write it in the decimal notation. So the denominator, or in this case the 8, goes on the outside, and then the numerator, the 5, goes on the inside. Now the way this works is we say how many times can 8 go into 5? Well, it can go in 0 times. And so what we end up doing is we put a decimal and then a 0. And then make sure you put a decimal after that 0 we put down on top. Now the question is, how many times does 8 go into 50? Well, 8 goes into 56 times. And 8 times 6 is 48. And then we want to subtract. 50 minus 48 is 2. We're going to draw another 0 and we're going to bring it down. And we start the process over again. How many times does 8 go into 20? Well, it can go in twice. And that's going to give me 16. And 20 minus 16 is 4. We're going to do another 0 and bring that down. And 8 goes into 40 how many times? 5 times. And 8 times 40 is 40. So when I subtract this off, I end up getting 0. And once we either get to 0 or we see a pattern that's repeating, we can stop. So we've finished. We have our decimal up on top. The only thing we have to remember is that this was negative to begin with. So this is negative 0.625. We call this a terminating decimal because it ends. It has a stopping point. Let's try 7 over 11. We're going to do this the same exact way. 11 is going to go on the outside. And then we're going to have 7 on the inside. 11 goes into 7 0 times. And so we're going to add that 0. 11 goes into 70 how many times? Well, it goes in 6 times. 11 times 6 is 66. And 70 minus 66 is 4. So we're going to draw another 0 and bring it down. And we start over. 11 goes into 40 3 times. And 11 times 3 is 33. And 40 minus 33 is 7. So we're going to put another 0 and bring it down. 11 goes into 70 how many times? Goes in 6 times. And 11 times 6 is 66. And 70 minus 66 is going to give me 4. We're going to put another 0 and we're going to bring it down. And so are you seeing a pattern here? 11 goes into 40 3 times. We get 33. And then we end up with a 7. So we're just repeating this process over and over again. We either end up with a 4 or we end up with a 7 as our remainders. And so we're just going to keep getting 0.636363. So this is a repeating decimal that has a very clear pattern. And so the way that we write this is 0.63, and we put a bar over the piece that is repeating, which in this case is both the 6 and the 3. And this is called a repeating decimal. And so each rational number can be expressed in either a terminating decimal notation or a repeating decimal notation. And so every rational number has a point on the number line. However, there are some points on the line for which there is no rational number. These points correspond to what are called irrational numbers. And so the following are some examples of irrational numbers. Pi, the square root of 2, negative square root of 8, square root of 11, 0.1212122221, because there's no pattern that is repeating consistently. And so the set of irrational numbers is just the set of numbers that are not rational numbers. So you're either one or the other. So decimal notation for rational numbers either terminate or repeat, but decimal notation for irrational numbers neither terminate nor repeat. So they don't have a pattern and they keep going forever and ever. And so the rational numbers and the irrational numbers together correspond to all the points on the number line, which what makes up the real number system. And so the set of real numbers is the set of all numbers corresponding to the points on a number line. And so you can see below We have our natural numbers, 1, 2, 3, and 4. The whole numbers, 0, 1, 2, 3, and 4. The integers, which is all the -4, -3, up to 4. Then we have our rational numbers, which fall in here, and then irrational numbers as well. So this entire number line is the set of real numbers. And so the figure below shows the relationship among the different kinds of numbers. So starting with real numbers, you branch off into either a rational number or an irrational number. Irrational numbers don't have any other subsets. But rational numbers can either go to integers or rational numbers that are not integers. From integers, we have our positive integers, we have 0, and we have negative integers. So you can kind of see the hierarchy that comes into play when we talk about real numbers. Let's talk about order. So real numbers are named in order on the number line, increasing as we move from left to right. So for any two numbers on a line, the one on the left is less than the one on the right. We use the symbol less than. It looks like a gator mouth. So the sentence -8 is less than 6 means -8 is less than 6. The symbol that goes the opposite direction is greater than. And so the sentence -3 is greater than -7 means that -3 is greater than -7. And these are called inequalities. So let's go ahead and plug in the right symbol to make these a true sentence. I have 2 blank 9. So is 2 less than or greater than 9? 2 is less than 9. What about -7 and 3? Well, -7 is negative and 3 is positive, so it's definitely less than. -18 and -5. This is when people start to get a little bit confused. So if we're looking at two negative numbers, the bigger number is more negative, which means it's less than. So -18 is less than -5. You want to think the opposite when we're talking about negatives. And then -2.7 and -3.5. It would be helpful if we got what -3.5 was in decimal form. And so we can type this on the calculator. That's going to give me -1.5. So is that less than or greater than? That is also less than because -2 is less than -1. And just as a side note, A is less than B also has the same meaning as B is greater than A. The gator mouth is opening to the B in both scenarios. So let's go ahead and write these in the opposite direction. So -3 is greater than -8. We could write -8 first and then make sure it's still opening to the -3. Same thing goes for the second one. We can write -5 first, and we want to make sure it's still opening to -5, and then A. So a helpful mental device is to think of an inequality sign as an arrow, with the arrowhead pointing to the smaller number. And all positive real numbers are greater than 0, and all negative real numbers are less than 0. So if B is a positive real number, then B is greater than 0. And if A is a negative real number, then A is less than 0. Expressions like A is less than or equal to B and B is greater than or equal to A are also inequalities. So that bar underneath just adds in the or equal to part. So let's write true or false for each statement. -3 is less than or equal to 5.4. Well, it's definitely less than. So this is a true statement. What about -3 is less than or equal to -3? This is still a true statement because we have that equal to bar underneath the inequality symbol. So -3 is definitely equal to -3. What about -5 is greater than or equal to 1 2/3? Well, -5, a negative is not going to be bigger than a positive number. So this is going to be a false statement. And the last thing we're going to talk about is absolute values. So from the number line, we can see that numbers like 4 and -4 are the same distance from 0. Distance is always a non-negative number. We don't drive -12 miles even if we're driving backwards. So we call the distance of a number from 0 on the number line the absolute value of a number. So the absolute value of a number is its distance from 0 on the number line. We use the symbol of vertical bars around x to represent the absolute value of a number x. So to find the absolute value, if a number is negative, its absolute value is its opposite, which means it's just going to be a positive number. And if a number is positive or 0, then its absolute value is just the same as that number. And so the absolute value of -7 is just going to be +7. The absolute value of 0 is just 0. And the absolute value of 3/2 is going to be 3/2.